Hello everyone, this is AE357 Petroleum Technology. This is a class lecture for Chapter 7, Hydroconversion. Hydroconversion is a term to describe all reactions or processes in which hydrogen will react with hydrocarbon. The hydroconversion can be classified into three types of hydroprocesses, including hydrotreating, hydrocracking, and hydrogenation. The first one is hydrotreating. It is about the way to remove impurity, including sulphur, nitrogen, oxygen, and metal traces by reacting those impurities with hydrogen. The second type is hydrocracking. Hydrocracking, in which that I think we mentioned this kind of reaction before in chapter 5. This kind of reaction is using hydrogen to crack down the feedstock to obtain lower boiling point range of products. And the last type of hydroconversion is hydrogenation reaction. This reaction is to saturate the olefinic and aromatic feedstocks. This table lists different kinds of feedstocks and the products after reacted with hydrogen. Examples are here. Naphtha, which contains trace of sulphur, will be reacted with hydrogen to get rid of sulphur, and the product is now ready for the reformer raw material. And again, sulphur, which maintain or contained in vacuum gas oil (VGO), can be treated by hydrotreating to obtain FCC, fluid catalytic cracking feedstock. In addition, aromatics in gas oil. The aromatic in gas oil can be cracked down to diesel or jet fuel in a better quality. Let's focus on hydroconversion and hydroconversion in terms of hydrotreating and hydrogenation first. The goals are to remove impurities, sulphur, nitrogen, oxygen, and metal trace to obtain good products that meet the standard. By the way, some unsaturated hydrocarbon can be adjusted for the saturated hydrocarbon products. And this is a figure show where hydrotreating and hydrogenation should be located and what kind of raw material are. In this case, we can have naphtha to be traded in hydrotreating. We can have kerosene that may contain some sulphur. We can have sulphur, nitrogen containing in the atmospheric gas oil, or even vacuum gas oil to be traded in hydrotreating. However, in the case of DAO, which is an abbreviation of the asfalted oil, can be added some hydrogen to this, and then it will get lighter before feeding into FCC. And also this can act like hydrotreating to get rid of some sulphur that may a little bit contained in the DAO, desulfured oil. Let's look at the chemistry viewpoint. We have the desulfurization to take out sulphur. On different forms like mercaptans, thiophenes, and other sulfide that are linked with the hydrocarbon. The similar reactions are to eliminate nitrogen and oxygen. So we call denitrogenation and deoxidation from palladium or even phenol and peroxides. However, we have to consider about the byproducts that came out, which are ammonia and water. In case of hydrogenation, olefin and aromatics can be hydrogenated. For other saturated hydrocarbon or naphthalene, for example. Actually, hydrogenation is very important reaction on the regenerated of the catalyst. When the catalyst is deactivated by coking deposition. I think we mentioned it before from the previous chapter. The reaction showing here is a coking formation, which is the reverse reaction of what we are talking about. The reaction of hydrotreating and hydrogenation prefer to take place over the catalyst. The catalyst-based alumina shows very good in accelerate the reaction, and the example are cobalt molybdenum, nickel molybdenum, or nickel tungsten deposited on or dispersed on alumina surface support. Catalyst is quite sensitive. It's quite sensitive to the metal deposition, which is one type that we have to concern. That's why we need a guard reactor to get rid of some metal trash before feeding all the feedstock into the reactor that contain this kind of catalyst. And generally, when we look at this table, the hydrotreating and the hydrogenation are exothermics, meaning that the higher temperature, we have higher temperature, the lower equilibrium conversion is. As we can see in the next slide, in this slide you can take a look from the plots of the K values as a function of temperature for different kind of reaction A, B, and C. All reactions showing here are hydrotreating processes. So when the temperature increase, this x-axis is a temperature reciprocal of 1000, which increase in this direction into a move to the left hand side, will give the lower value of the K, big K, equilibrium conversion, equilibrium constant. Right. This is an example to provide you to understand about the temperature and pressure effects on the hydrotreating system. The result of this will tell us what the condition. This is the result, but later I will demonstrate how could we get this kind of result. This result can tell us about what condition we should use to operate. The reaction that we are consider here is the dehydrogenation of cyclohexane to benzene, or the other word is hydrogenation of benzene to cyclohexane. If the Gibbs free energy according to this, the way of writing here, is equal to 200,000, 100, and 100 minus 396 multiplied with temperature. Let's do a plot of equilibrium mole fraction on both benzene and cyclohexane. This is another example that be able to estimate. We would like you to ask you to find out how much the catalyst volume required and used for the hydrodesulfurization to reduce sulphur from 2.3 to down to 0.1 weight percent. In order to do this, we should know what kind of rate expression is. So what the question given, what the question gives is that the reaction order is based on 1.7 in order of, and the rate constant is given in the function of temperature here. Now let's take a look in the process configuration for the hydrotreating process. Okay, we have liquid feed, which will be mixed with hydrogen at this point and fed into the heater trains, including some exchanger, some furnace, before feeding into a fixed bed catalytic reactor. The effluent, of course, will be cooled down by exchange heat to the preheat system. And hydrogen rich gas is separated because some hydrogen may not react. Will be separated using high pressure separator. Before hydrogen is recycled back to the system, it requires some treating process. Otherwise, hydrogen sulfide may be mixed, feed back to the system. The liquid effluent of the reactor is introduced into distillation column for the separation of different product range. We do have to consider about how much hydrogen have to be made up, and also how much hydrogen or some small hydrocarbon molecule need to be purged out. We have mentioned about the makeup hydrogen. So the makeup hydrogen is a compensation. It's a compensation for the amount consumed, because of course some hydrogen may consume, and we need to add up the hydrogen into the process to maintain the pressure inside the reactor during the run. It can be calculated according to this equation. Now we look at the diagram that may help you to understand easily. Hydrogen need to be fitted here to react with the heavy hydrocarbon. And after that, the heavy hydrocarbon become light hydrocarbon. And of course, some dissolved hydrogen maybe occur and then go with the product. And of course, we need to purge the hydrogen out in some way to prevent the accumulation of C1 up to C4. So the equation is how much that we make up will equal to the number that we feed in minus the consumption from heavy to light, and then minus the purge and minus the hydrogen dissolved. So far, we can now conclude that the condition that favorite for hydrotreating, three factors are high pressure based on hydrogen that feed in, high temperature, and high surface velocity. This table presents that how high on both temperature and pressure are depend upon what kind of feedstock are. Also, it gives the idea of spare velocity. The spare velocity here, SV. This stands for liquid hourly spare velocity in terms of a reciprocal of time. Students need to think about what does it mean by the LHSV equal to here in the unit of a reciprocal term in the class. Moreover, you can see that hydrogen is fed in the high excess according to the ratio of hydrogen and hydrocarbon. We need a huge ratio of hydrogen to hydrocarbon. One is to keep the pressure high enough. And to work on the hydrogen supply to the system, we do have empirical equations for the preliminary calculation. Of course, what we have to know first is how much sulphur is maintained in the feed, and then we can calculate for the hydrogen that will be used in the reaction. Then we can tell how much that the oil or the product will change in terms of API degree. And we have known that the API can be calculated for the K value. The K value is the UOP Watson characteristic factor. And from this, when we plug into the equation, we can tell roughly how much the paraffin, naphthalene, and aromatic in terms of volume percent will be presented in the products. Now come to the examples to make sure that you understand. So we need to determine how much the hydrogen used in the system when we have naphtha that feed into with sulfur dioxide equal to 1 and also the API equal to 50. Okay, we have done the understanding of hydrotreating and hydrogenation, and now we are coming to hydrocracking. See, we finished number 1 and number 3, and now we come to number 2. Actually, we have discussed about this before in chapter 5 in the textbook. Hydrocracking is, to convert high molecular weight of feedstock to low molecular weight of products. The catalyst required here should be in bifunctional duty 1. Hydrocracking are located to receive gas oil, either from both from ADU amorphic distillation column and also VDU vacuum distillation unit. Hydrogen fed into the reaction is also used to treat or remove sulfur as well. So low sulfur fuel oil can be produced. So they do two reactions at the same time, one cracking and one removal, one cracking and one removing some contaminant. And of course, the products of the hydrocracking will be lighter than the one in the feedstock. Naphtha is lighter than kerosene, and naphtha is lighter than the diesel one, as we knew before. For example, you can see that most feedstock will get cracked down to smaller complex like naphtha. Most of them are naphtha. Reactions which are involved on the hydrocracking are state chain cracking. We get smaller molecular hydrocarbon products, and also we dealkylation and ring opening. Now when we look at kinds of reaction here, you can make some conclusion that hydrocracking is the reaction that will produce more product, not in terms of octane number improving. Hydrocracking catalytic function is provided by acidic support, whereas dehydrogenation and hydrogenation function is provided by active metals. So we have support and metal. So we need some cracking by the acid side, active side, acidic active side, and also metal for the hydrogenation and dehydrogenation reaction, as we mentioned before. Now take a look at the process configuration. in the process configuration here, this is a one step. Actually, we do have just two steps. So students need to read the textbook for more information. A commercial cracker will convert the feedstock for about 40 to 80%. However, a high conversion is required. The product from the bottom of the distillation tower can be, regenerate. The configuration can use to maximize the diesel products, and is employed by the amorphous catalyst. But the final thing that we have to mention about the hydrocracking is to make the material balance for that hydrocracking. This is the hydrocracking correlation empirical for yield that can use as a preliminary calculation. Let's see the example. We would like to, in this case, the feed is vacuum gas oil that will be collected, I'm sorry. So in this case, the example showing will show here is the feed of vacuum gas oil that have the API of 20, and also the average boiling point of 75 degrees Fahrenheit. We would like to do some material balance around the hydrocracker, and later I will show you the demonstration.